Welcome to this 4-part tutorial on how to create a rock-solid touch design using CapeExt's virtual prototyping environment to find design flaws and validate fixes. The tutorial will cover debugging of simple capacitive touch designs with a flat overlay, all the way to advanced designs with 3D CAD models. Along the way, we will estimate the time used in a physical prototyping environment and compare with the time spent with virtual prototyping to demonstrate what this means to your design time. The tutorial has 4 parts. 1. That is this video. Project introduction. How to build a simple virtual prototype with flat overlays. 2. Identify undesired touch behavior and correcting them in the PCB layout, and then validating the corrections. Part 3 explains the 3D model theory that CapeExt is built on, and we're going to demonstrate how to build a 3D virtual prototype and obtain the first touch results. And then in chapter number 4, we're going to compare 2 strategies for improving the design. So let's start with chapter number 1 of this tutorial. The design example we will be using is a Bluetooth remote controller. The application is powered from a CR2032 battery, and it uses a microchip AT-SAN D21E MCU for touch and a Nordic NRF52832 SoC for Bluetooth low-energy communication. To simplify the example, the design only contains necessary signals for touch and chip-to-chip communication. The design contains a thumb-operated trackpad for controls and a grip sensor that senses when the product is picked up or put down to control power on and off. However, before we do a virtual prototyping of the complete design in 3D, let's validate the PCB design in a simpler environment with fewer variables. This also is quicker in CapeExt. This means that we will, for now, ignore the 3D design and let CapeExt put a flat overlay on each side of the PCB. For any type of virtual prototyping, CapeExt will need the Gerber files for the PCB. The files absolutely needed are conductive layer files. This is a 2-layer PCB, so only the top and bottom layout files are needed. Drill file for CapeExt to understand where the vias are to connect the layers. Keep out layer, which defines the dimensions of the board. We also recommend that you export the silkscreen overlay files. Although not needed for the simulation, they make it easier to understand what part of the board you're looking at. Once the files have been created, we import them into the CapeExt environment. Let's start by selecting New Project. This throws us directly into the File Import wizard. Here we import all the files we created. We click Add Layers and select the 6 layers representing our PCB. For all Gerbers that are not layout files, CapeExt wants you to confirm it has interpreted them correctly. This is necessary as no standard file extensions for Gerbers exist. Once imported, it is important to verify that all our touch electrodes are represented accurately. If we click Simulation Options, we can mouse over the electrodes and see that they appear to be correct. First, we check the grip sensor. We see that both electrodes for the grip sensor are identified. The same for all 4 X electrodes in the trackpad. However, the Y electrodes have a problem. Clearly, 2 of them are connected together. The reason for this is that we imported the Gerbers with too low resolution, and a short circuit occurred in some of the marginal sections of the PCB. Luckily, this can be fixed. We will re-import the files, and this time, Rather than going with a default resolution of 600 dpi, we will select Auto Detect. This function analyzes the PCB, and in our case, suggests 970 something dpi resolution. The reason why Auto Detect is not default is that it in rare cases overestimates the resolution required. This can result in long computation times or CapeExt running out of memory. Should this happen after you have selected Auto Detect, you need to manually find a resolution that works. Fortunately, Auto Detect works in almost all cases, and with most PCBs, even the default 600 dpi is sufficient. A quick mouse over reveals that all the electrodes now have been interpreted correctly by CapeExt. Note that CapeExt doesn't know where the touch electrodes are located, so every copper net on the board is assigned an electrode name. So we will identify the touch electrodes and give them names that make them easier to identify. To change the name of an electrode, click on the electrode on the board to highlight it in the list. Then click the name to type in the new name of your choice. There, all the electrodes have been renamed from their default designators. Once we have done this, we can click Hide Electrode with default names to make the list a bit more manageable and readable. Now, in order to evaluate the performance, we need to apply some dielectric layers over the electrodes. Otherwise, our results will not be useful for a first-order validation of the board. In general, capacitive touch requires a non-conductive overlay that separates the finger from the touch electrodes. The remote control has a maximum thickness of 10 millimeters, but this varies. We will add overlays of 3 millimeters thickness to both sides of the PCB. That should work well for a rough validation of the touch performance. For a board that doesn't have complex 3D structures that are affecting the touch design, this is how you will evaluate the design in its entirety. So for users that don't need the design to be prototyped in a 3D environment, this tutorial video 1 and 2 should cover most of your design flow. Most designs do not have touch on both sides of the PCB, and for these designs, adding a single overlay on the top part of the PCB is sufficient. First, we will add the top dielectric layer. Click on the top copper layer and then select Add Layer above. Our only option here is to add a dielectric layer. We select a thickness of 3 millimeters and set the material to plastic to give it the correct electric permittivity. We'll repeat the process for the bottom layer. And now we can see that these two layers are added to the PCB. However, it appears that they both ended up on the overside of the PCB, but clicking Apply Changes fixes this. You are advised to click this every time you do a change in the project editor. And there, both our overlays are in place. Please note that you can add as many layers as you want on both sides of the PCB, combining different materials to simulate complex stack-ups, including air gaps. The most useful way to perform a touch simulation is to use area touch. This function provides a heat map showing the touch signal strength for a specific sensor over a user-specified grid. We enable this function by first enabling the touch probe, then enabling area touch. By default, the area is the same size as the PCB, but can be extended if one wants to check the response on the touch also outside of the PCB area. The resolution of the grid can also be changed, but we'll stick with the default setting. Now, we need to select which electrodes we are interested in evaluating. This design contains no self-capacitive sensors, so here we can save some simulation time. By default, CapeExt calculates the capacitance of an electrode relative to every other electrode in the design. And since the capacitance between a X electrode and a Y electrode is the same, no matter which of the two electrodes you measure from, you only need to simulate one of them. Our trackpad contains 4 X electrodes and 9 Y electrodes. We therefore save a lot of simulation time, by simulating the X electrodes only. Hence, we will select X0 through X3 and grip sensor X as the electrodes we want to simulate. Once this has been done, we click Run Simulation, grab a cup of coffee, sit back, and let CapeExt do its thing. And that completes tutorial number 1 in this 4-part series. You now know how to build a basic virtual prototype in CapeExt. In Chapter 2, we will look at how to measure the touch response and how to correct any design weaknesses that we find.